All right, so this is a nice video that kind of just summarizes everything about inference that we've been learning over the last couple weeks. That way you could be prepared for your big test coming up. All right, so let's make sure we really understand what inference is. It's trying to estimate something about a population through a sample. So again, we're just trying to make an educated statistical guess about a population parameter based on a sample statistic. We're not knowing, but we are inferring. So here's a couple examples I came up with. I estimate the proportion of high school students that wear glasses is somewhere between 23% and 34%. Or I estimate that the mean IQ of a high school student is somewhere between 96 and 135. Again, I don't know the true proportion of high school kids that wear glasses. I don't know the true average or the mean IQ. These are just confidence intervals that we've learned about that give us an estimation of what that truth can become. And that's what inferring is all about. Here's two more examples. I was told that 7% of clovers have 4 leaves, but based on a sample, I have significant evidence that it's less than 7%. I was told that the mean amount of time for a baby to walk is 11.6 months, but based on a sample, I have significant evidence that it is more than 11.6 months. So again, these are the results of a significance test, which we have also learned about. The idea is that we thought something was true, but then based on a sample, we learned that maybe it wasn't, and maybe we did have significant evidence that it was something else, like these two examples explain. The process is actually extremely simple. We make inferences about population parameters. Population parameters comes in two forms, either population proportions P or population's means mu. And these are two values that are true for the entire population, so we oftentimes do not know them. So we make inferences with sample statistics, such as sample proportions, like a p hat, or sample mean x bar. So the whole process is, again, like we've talked about in class, really makes a lot of sense. We don't know what the true proportion is, so we're going to use a sample proportion to try to estimate what that true proportion could be. Same thing. We don't know what the true mu is, but we can use a sample statistic, x bar, a sample mean, to try to estimate what that mu is. So again, we're trying to make inferences about population parameters with sample statistics. So that's the whole idea of this entire overall unit. All right, but first we need to understand something extremely simple. We must understand the most important aspect about a sample statistic is that it will vary. Remember, that's the one thing we've always been saying, is that samples vary. If you think about gathering a sample of people, I mean, there are hundreds and millions and probably even more than that, samples of people. And it's impossible to know all of them, but we do understand that samples themselves are going to vary from one to another. So we call this variation the standard deviation of a statistic. But remember, sometimes we have to approximate that standard deviation with some information from our sample, which is why we might call that standard error. But essentially, it's the same thing. And remember, the big idea that we learned is that the bigger samples vary less from the truth. This is the whole idea that when you're sampling, bigger samples are better, right? Because a bigger sample is always going to be closer to what the truth actually is. A smaller sample has the opportunity to vary more and could be really, really far from what the truth actually is. All right, so let's make sure we truly understand how statistics vary. So, proportions. How can a standard deviation of a sample proportion? How could one proportion deviate from another, right? How could samples deviate? Well, the formula for the standard deviation of a sample proportion is giant square root P times 1 minus P divided by N. And remember, P is the true proportion of the population. But in most scenarios, we don't know what that is. I mean, listen to me. If you do know what the true P is, please use it because you're going to get a much better value. You're going to get the standard deviation. But in most cases, the only proportion we know is that of our sample. So instead of P, we use P hat and then 1 minus P hat in that formula. When we do make that shift, though, we have to call it the standard error of the sample proportion. Same thing can be said for means. The standard deviation of a sample mean is sigma divided by the square root of n. But remember, sigma is the standard deviation of the entire population, which we're never going to know, right? I mean, again, if you do know it, maybe the problem does tell it to you, please, by all means, use it. But in most cases, the only standard deviation we know is S, the standard deviation of our sample. So if we replace sigma with S, the standard deviation from our sample, and divide by the square root of n, we get what's called the standard error of the sample mean. Now, all of these values just allow us to understand that samples are going to vary, which allows us to build that really pretty model, right? The normal model. So we build this model, sorry, it's a little slanted here, and right smack dab in the center goes the truth, whether it be the true proportion or the true mean, and then we say, all right, when we take samples, not every sample is going to be exactly smack dab at that mean, at that center, at that true proportion. I mean, it could be, but chances are it might be a little higher or a little lower. So there is going to be that variation there. All right, now that we've now that we've recalled what inference is all about, I want to make sure you understand that there are 9 different scenarios, 9 different types of problems that could pop up, all dealing with inference. They relate to either a confidence interval or a significance test. So remember, a confidence interval is when we're trying to estimate a population parameter. And again, we don't know what those values are. We're trying to find the true p, or we're trying to find the true mean mu. We don't know what they are, so we're trying to use a sample to estimate them. A significance test is where somebody tells us that they know the truth, or that they think they know the truth, and we want to see if there's evidence to claim something otherwise. And this is where we need the hypothesis, the null, and the alternative, and all that fun stuff that we've learned about as well. All right, now let's briefly remind you of what a confidence interval is all about. A confidence interval involves 4 steps. The first step is to explain what you're trying to estimate. So just tell me. Now that's always going to be in the problem, because the question in the problem is going to tell you what you're trying to find. So you're just kind of repeating it. Then you got to check those conditions, which we all know and love. And then we have to find the actual interval, which is taking your test statistic, going up and going down by your margin of error. Now, the margin of error is a combination of your critical value, which is, again, either your z star or your t star, depending on if you're working with proportions or means, and then the standard deviation of your statistic. Well, usually we cross that deviation out and we call it standard error, and that's okay, and that's just what we've already talked about. Standard deviation and standard error are very similar. It all depends what information you're using. So as we just mentioned a couple slides ago about standard deviation versus standard error. And then the 4th step is to please interpret your confidence interval in context. All right, here are the 4 basic steps for a significance test. Step 1 is to give your null and alternative hypotheses. Step 2 is to check your conditions, which we all know and love. And then step 3 is to do the work. Remember, the work involves 3 steps. Draw your model, find your test statistic, which we call a z-score or t-score. So basically, you're locating your evidence to see if it is significantly high or low. And then you're going to find the p-value, which is the probability of your test statistic occurring or more extreme. So we have to find that as well. And remember, we're going to use normal CDF or TCDF for that. And then you have to make your conclusion. Do you reject a null or do you fail to reject a null? Now, I want to remind you that I've created all types of cheat sheets for this. So, for example, I've given you a cheat sheet that covers everything you need to know about confidence intervals. It goes over all the specific details for a confidence interval for a single population proportion, a single population mean, and then on the back of this, remember that it went over all the steps for trying to find a confidence interval for the difference between 2 proportions, or down below here, the difference between 2 means. So please make sure you use these cheat sheets because they'll really help you. We also have a cheat sheet that I gave you over how to conduct a hypothesis test. So step 1, create your hypotheses. Step 2, check those conditions. They're all there. Step 3, draw the picture, locate your z or t score, and then find your p-value. And then make your conclusion, all based on your level of significance alpha. Again, we've talked about all of this, and then I'll show you one more cheat sheet that we had, and that was the cheat sheet for the difference between 2 population proportions. So again, the hypotheses when you're comparing 2 proportions, the conditions, all the work when you might have to pool, or if you forget to pool, it's really not a big deal. And then your conclusion. And on the back of that cheat sheet was all the same information, but for looking at the difference between 2 population means. So the point I'm trying to make as we go back to the PowerPoint here is that we have tons of cheat sheets to help us remember all these steps. This is nothing more than a review video to make sure you remember how to do it all. All right, let's go through the individual 9 scenarios very briefly. Scenario number 1, we're trying to estimate a population proportion with a confidence interval. This is called a one sample z interval. The whole idea is that we start with our sample proportion p hat, we go up and down by our margin of error, which is our z star times our standard error, and there's the formula right there for standard error involving p hat. Very simple. This is called a one sample t interval. This is used when we're trying to estimate a population mean with a confidence interval. Here we're going to start off with our sample mean x bar. We're going to go up and down by, again, our margin of error, which is your t star times the standard error, and there's the formula right there for the standard error. Then, of course, we have trying to estimate the difference between 2 population proportions. This is called a two sample z interval. And here we're going to start off with our observed difference, right? This is the difference between our 2 samples 1 and sample 2. And then we're going to go up and down by our margin of error. Once again, that's z star times standard error. And there's the formula for standard error. Now, we did talk in class where this formula comes from and why it is the way it is. So hopefully you remember that as well. All right, then we can estimate the difference between 2 population means. Basically the same idea. This right here is the observed difference. What was the difference between our 2 sample means, sample 1 and sample 2? Then we're going to go up and down by our margin of error, which is your t star times our standard error. And once again, here is the formula right there for the standard error between the difference. And again, we talked in class about where that formula comes from. All right, up next is to determine if there is a significant evidence for a claim about a population proportion with the test. All right, just to briefly cover this, this is called a one sample z-test. Remember, this is where somebody says, hey, I read that 50% of people get enough sleep. And we think, really? I think that it's more than 50% of people get enough sleep. So then we have to create our model where we put the truth 50% in the center, and then we use our evidence to either show that it's more or less or maybe just something different. And again, all that has been already outlined for you. This is just something else that we should know how to do. Same thing here, determine if there's a significant evidence for a claim about a population mean with a one sample t-test. Same idea here. Somebody claims that the true average diameter of a melon is 133 millimeters, and we think that, we're wondering maybe it's something different, like maybe it's not 133 millimeters. And then we conduct a test. We make our picture of our model, and we look for our evidence. Again, we've learned how to do all that. This is just a type of problem that you need to be ready for. Now, what else? Determine if there is a significant difference between 2 population proportions with the test. This is what we've done most recently. So we want to see, is there a difference between 2 proportions, right? Is there a difference between the proportion of men that do something and the proportion of women that do something? So our null is that they're the same, and the alternative is, no, we think the proportion for men is higher than the proportion for women, or something along those lines. And then it's all about looking for that evidence. And then the same thing can be said to determine if there's a significant difference between 2 population means. It's all this same idea, right? The null is that the mean for men is equal to the mean for women, and the alternative that we're trying to explore is that maybe the mean for women is more than the mean for men. And then again, we make that model and we look for our evidence. All right, so that covers the 8 scenarios that we talked about, but I did mention that there are 9 scenarios. So what is that 9th scenario? Well, it's one that we've actually already talked about once in class. It's just been a while. Here we need to determine if there's really a difference between paired data with a test. This is called a one sample paired test. Now, this entire problem behaves just like a traditional one sample test for means. The idea, though, is that the data came from one sample that was simply paired together. So this is not a different type of problem, it's just disguise. It's going to look like there's 2 sets of data, but there's really only one set of data from one sample. And to give you a chance to see this, here's an example. So here we had 9 subjects, and we wanted to see if a new weight training program would help make them stronger. So we have one group of 9 subjects. We measured their strength before and after a strength training program. So again, it looks like we have two sets of data, before and after, but we really only have one set of data. The one set of data that we care about is the difference, because all we care about is showing, is there a difference? Did this program make a difference? So all we would care about would be, for example, the 4 kilogram difference from before to after. Right here would be the 15 kilogram difference to 6 kilogram difference. And again, the point I'm trying to make is that we just care about the difference between these numbers. So it looks like there's two sets of data, but there's really only one. So the null hypothesis would be that the average difference is 0, and the alternative would be that the average difference is greater than 0. Because if the average difference is greater than 0, that would show that these people gained weight, or that, they gained strength, which means they could lift more weight. So again, we would treat this just like a one sample test. All we would care about is the average difference. We would need the standard deviation of that difference, and then we could build our model. So we treat this just like a single sample, but it would be all about looking at the difference. So watch out for these. It's called paired data because like the 3 and the 7 are paired together. They're from the same person, just measured before and after. The 7 and the 19, they are paired data. They came from the same person. They're just measured before and after. So watch out for problems like that as well. All right, the other important things that we learned about overall in this unit was thinking about error. There are 2 types of error. Type 1 error, the null hypothesis is true, but we reject it and think the alternative is true. Now, for the first time, we're going to talk about the fact that the probability of making a type 1 error is called alpha. And yes, that is the same alpha as your significance level that we already learned about. So for example, when we typically, when we typically set our alpha level to be 0.01, that means in a particular problem like that, there's a 1% chance that we might be making a type 1 error. Or if we decide to use an alpha level of 0.05, now there's a 5% chance of making a type 1 error. Now remember, I'm still not going to have you worry about did you make a type 1 error, did you not make a type 1 error. It's really more hypothetical, but there is always the possibility that you made the wrong conclusion. It doesn't mean your work is wrong, it's just a hypothetical scenario that in the real world, maybe we made the incorrect conclusion. Now a type 2 error is when the alternative hypothesis is true, but we fail to reject the null. So the alternative is true. We should have rejected null, but we didn't. Now the probability for this is called beta, which is the Greek letter beta. It kind of looks like a B with a little extra tail on the front there. But don't ever worry about calculating beta. I'm never going to ask you, nor is the AP test ever going to ask you what beta is or how to find it. Just understand that the letter beta does represent type 2 error. Now, the important thing I skipped a slide. Errors always work against each other. So if we try to lower alpha to decrease type 1 error, we are at the same time increasing our chance of type 2 error, or vice versa. So I kind of drew these little arrows to make sense of this. So if we try to lower our alpha to say 0.01 to try to decrease type 1 error, then beta automatically goes up. Now don't worry about what it goes up to. It doesn't go skyrocketing up to like 70% or anything like that. It's still low in of itself, but it does increase a little bit. So when you try to lower type 1 error, then your chance of type 2 error goes up. Same thing can be said the opposite way. If you try to increase alpha, maybe to like 0.05 to try to increase the risk of a type 1 error, well then the good news there is you are going to lower your chance of a type 2 error. So these errors work at opposites of each other. Okay, it's not directly a one-to-one opposite type relationship, but the point is if you lower your type 1 error, then you are going to have an increased type 2 error and vice versa. All right, now the last major thing I want to talk about is that if the null is wrong, we want to reject it, right? I mean, this is doing the right thing. If your null hypothesis really is incorrect, we want to find evidence to reject it and go with the alternative. The probability of correctly identifying the null hypothesis as wrong and taking on the alternative is called power. So yes, power is a true statistical term, right? It doesn't mean, it actually has a definition of power related to statistics. And again, it's literally the probability of making the right decision, the probability of rejecting a null when the alternative is true. That's called power. So when you do the right thing, when you reject a null and you're supposed to, that's when you call power. It's kind of cool that that's an actual term in statistics. Now, this is the complete opposite of type 2 error. Because in type 2 error, we should have rejected the null, but we did not. Remember, in type 2 error, the alternative is true, but we failed to reject it. So power is not making a type 2 error, right? Power is the alternative is true, then we should be rejecting the null and going on with the alternative. So it's just a term I'd like you to know. Now, we always want more power, right? I mean, who doesn't want more power? So a big AP question that I've seen in the past is, how do you get more power? The number one answer is increase your sample size. A bigger sample will always do a better job of showing us the truth, since bigger samples vary less. I mean, just think about that for a second. If you want a better way of seeing what's true, a bigger sample should reveal that, because a bigger sample is always going to be what's true. Let me just kind of demonstrate this with a real quick example. If my null is that the true mean is 8, and the alternative is that it is more than 8. All right, so power says this. If the alternative is true, I want to reject the null. I want to conclude that the truth is more than 8. But a bigger sample will help me see that better. So let's just say the truth is really 9.2, right? But I don't know that, because whoever really knows what the truth is. But a small sample of maybe only 10. A small sample has a lot bigger chance to vary. So a smaller sample might end up being closer to 8, which would make me think 8 is true, but remember, it's really not. 9.2 is true. But if you have a really big sample of maybe like 500, a bigger sample is going to gravitate closer to what the truth is. So a bigger sample will show me that the truth is something near 9.2, which would help me reject the null and go with the alternative that it's really more than 8, since it is. So that's the idea of why bigger samples are always going to help us see the truth better, which would help us have more power. Now, the probability of power is 1 minus beta, because remember, it is literally the complete opposite of beta, because beta is type 2 error. And type 2 error is when we make the mistake of not going with the alternative when we should. So power is not making that mistake, it's doing the right thing. So that is why the opposite of beta, 1 minus beta, is power. So look at this final picture I have for you here. How could we get more power? Well, if we increase alpha, remember that we already talked about, that's going to decrease beta. And if you have less beta, you're going to have more power, because beta is the probability of type 2 error. So if I can get that to go down, then I'm naturally going to have more power. And that's the ultimate goal here, is to have more power. So how do you get more power? Have a bigger alpha value. Now, a bigger alpha value does have an increased risk of type 1 error, but hey, all we care about is having more power, right? So if you increase alpha, you will have more power, but the better way to have more power is really to increase your sample size. Bigger sample sizes literally solves everything. A bigger sample size will always closely reveal the truth and make you more accurate. And that goes all the way back to a topic we learned months ago. So that's kind of a quick review about everything you need to know about inference. Make sure you know the general idea of what it is. Make sure you could solve any of the different 9 scenarios that I could ask you about using confidence intervals or significance tests. Please reference those cheat sheets. That way you remember all the steps and follow them correctly. And then don't forget about type 1 and type 2 error, and make sure you know about this new idea called power. All right, guys, that's it. With all this knowledge, you should be ready for your tests.